Namaste. Welcome to my introductory physics class. We are going to do lab work related to interference experiment, right? So without any delay, let's go into our theoretical part or introducing some parameters related to this interference experiment, right? So, let's go into the brief introduction of interference experiment. Double slit interference, it means interference or property or an important property of light using double slit. So the name is double slit interference experiment. And we must know uh, beforehand terminologies related to double slit interference pattern. So these are the some of the patterns we are going through in the for beginning of this introduction. So one is path and another is phase. So let's define what is phase and what is path. Now I'm considering a particle which has been started, which is going to start from this origin or initial position is O, and it can travel y as well as x direction. So it has two-dimensional motion. So it doesn't travel straight towards the x, or it doesn't travel straight towards y, but it can travel in both directions. So in the first, in the beginning of that is motion, it is going uh, along this line, and then after some time it reaches to b, and then it again reverses its path towards the negative y direction, and then negative y direction, and then again it returns back to the initial position. So if we allow the motion of the particle in this way, then it will again retraces is the original path, right? So it is going again, or it is following the same pattern like this. So let's consider this an example. I'm just giving you an example, but this is just an analogy. After dealing with these things, and then I'll give you the wave pattern of interference, because without utilizing the property, an important property of light that is acting as a wave, we cannot define interference, because for interference we must know the wave nature of light. Wave nature of light is important in interference experiment, right? Because particle nature cannot give you the interference pattern. Yeah, why light does not give you interference pattern when you take light as a particle? I'll give you some example, I'll give you some reasoning behind it, right? So but before going to this particle nature or wave nature, let me give you this example. So the particle has been started from O, and it has reached to D, traveling along this line, right? If you look at the figure, you can clearly see it. Now, the definition of path part is the linear displacement traveled by a particle. So when that light travels from O to A, suppose O to the maximum point in y direction, in positive direction, because above this line we consider the motion to be, or displacement y direction must be taken to be positive, and below this line y direction is taken to be negative, or y displacement is taken to be negative. And uh, as we know, so towards the right, or towards this direction, the x direction is positive, and towards the left, from the O to our towards the left from the O, the x direction is taken to be negative, right? So if you look at the definition of path, it is the linear displacement traveled over a particle. Now, when the particle started from O reaches to the maximum point in the y direction, that is also considered, that is also said to be the crest, right? So from the mean position, it is the maximum displacement. Crest is defined to the maximum displacement in the positive y direction. So when the particle starting from O reaches to the crest or maximum point in the y direction, then it will analogical, or it in displacement vector, we can consider that light has traveled O to A only. That is defined to be the path, right? So because it is the linear displacement, so the linear displacement is O to A, and it is the path. When the light comes to the mean position again and it reaches to B point, so the linear displacement is OB. And when it goes into the negative y direction, the negative maximum displacement in negative y direction is known as tau. So it reaches to C, because when you take linear displacement, it simply reaches to C. So the linear displacement, or the path traveled by the particle when it reaches to the tau position, is O to C. And when it again return back to its original position or mean position, then the light travel by the particle from initial position to the final position d, because after this the particle is repeating its motion. That is our consideration. So the displacement from O to D is known as the lambda, or it is the path traveled by the particle in a complete motion, right? Because after this the motion will be repeated. So if we talk in terms of angle, and that is called phase. Phase is simply angle, and it is defined as it is the angular displacement traveled by a particle, right? So when the light completes its one complete cycle, then or when a particle completes is one complete cycle, then it covers 360-degree angle or 2 pi radian, right? So this is the phase or angular. You got me? Now I have given you all the parameters related to the particle in two-dimensional motion following this sinusoidal motion, right? Now if we consider wave to this medium, let's consider transverse wave, because we are not concerned with the longitudinal wave, because light is not a longitudinal wave. From the experiment we proved that that light is a transverse wave. So when the transverse wave travels through this medium, then the wave will have the same form, the vibration of the particles in the direction of in the direction of propagation of x, that is in the direction of x, will have same vibration of particles like this, as shown in the figure. Even though we considered in the beginning it is the motion of the particle, but when the light, because the transverse when the transverse light passes through the medium, then it will cover similar motion, or the vibration of the particles will be the similar in the direction of propagation of the wave. That's why even though I gave you the example in the beginning with the motion of the particle, but it can be equally valid to the uh, transverse wave for a light, right? So this is the and for that case, lambda is known as wavelength of the light. 2 pi radian is the phase angle related to the wave. And 360 it is in degree, but we have to take in radian system. To 2 pi that is equivalent to 2 pi, and 2 pi is equal to phase angle of the wave. And so now crest, in terms of crest, this crest is the maximum positive displacement in the y direction, and this straw is the maximum negative displacement in the y direction. You know the what is crest, what is straw, what is the wavelength, and phase, right? Now let me tell you the path difference or phase difference. Now if we consider the particle at O and B, then they will having the path difference, because O and B are not at the same distance. They have the certain path difference. Even though they are at the same position, but they do not have the same path. That's why they will have the some difference in the path, and this one is zero, and this B is half of this one, lambda, right? So lambda by 2 is the path difference between them. Now if we consider this one A position, then the particle at O or particle at A will have certain path difference, and it is half of this lambda by 2, and it is will be lambda by 2, one half of the lambda by 2, that is lambda by 4. Now if we take the C, then O and C will have path difference of 3 lambda by 4, right? Now if we take a complete one, then it will be the lambda. So these are the part difference. And if we talk about phase angle, phase difference, then this O and D will have a phase difference of 2 pi radian, and this O and A will have phase difference of pi by 2, and this one is pi. O and B will have phase difference of pi, and this one will be 3 pi by 2, right? So these are the part difference and phase difference. Let's go into the coherent sources, because in order to explain interference experiment, we know the meaning of coherent sources. So two monochromatic sources are said to be coherent one if they have the same frequency and have constant phase relationship to each other. Because I already told you what is phase difference, and what is phase, and frequency. Because frequency is the number of repeated cycles in unit time, right? So if you look at the previous one, this one is one cycle, one crest, and one trough makes a cycle. If it is done in 1 second, then its frequency will be one cycle per second in a SI unit. So this is 1 hertz, or cycle cycle per second frequency wave. So frequency is nothing, it is the number of complete cycles completed in 1 unit second of time, right? So frequency, and constant phase, I already told you. So for coherent sources, uh, it must satisfy two conditions. One is same frequency. The two waves must have same frequency and must have constant phase relationship to each other. It means for certain duration of time, let's say for 5 seconds of time, it has some certain part difference or phase difference of 90 degree, but after 5 seconds the phase difference changes to 180 degree. Then these two coherent, so then these two sources are not said to be coherent one. For coherent one, they must have same frequency, means all over the time they will have the same frequency. It means 10 revolution per second or something like that. And for and they must also satisfy the constant phase relationship. It means throughout the time they must have the same frequency, like 10 revolution per second or 10 cycles per second, and 90-degree phase difference, or the phase difference between them must be 90 degree or 0 degree at all. This can also be true because the constant phase relationship is so they must satisfy these two things. And let's go into the superposition principle, right? So when two or more waves overlap, the resultant displacement at any point and at any stand is found by adding the instantaneous displacement that would be produced by individual waves if each were present along at that point. So let me give you an example related to this one. So these two waves are going to interfere with each other, or they are going to overlap with each other. Then it has certain displacement, because now if you make this reference line as I showed you in previous slide, and it will overlap to each other, then we will have this one final resultant wave, right? So this is according the principle of superposition. The displacement, or this is the y displacement we will have, or the resultant displacement we will have the vector sum of these individual displacements of these y's. So this is the principle, superposition principle. Now if these two waves have the same displacement, that means same amplitude or same crest, then same frequency, and then the resultant wave will have the double the amplitude or double the crest from the minimum position. Now if we consider this one as the second case, first wave and second wave. Now in this case, look at this crest is falling on the trough, this trough is falling on the crest of another wave. Now if we superimpose these two waves, then it will have no wave at all. The line will be linear one. It means the wave will be vanished, the wave will be vanished. And this is only possible if the crest of one wave falls on the trough of another wave, and so is the case with the trough with the crest. So this is only possible if they have the same amplitude and same frequency. As I already told you, coherent sources, this is only possible in case of coherent sources. But for any sources, the resultant cannot be always be equal to zero. This is only possible for coherent sources, right? Which is necessary condition for interference of light. One example where the amplitude is not going to be zero. So if I consider this as first wave, and another wave is of this one, and in trough there must be a crest, so like this. Now if you superpose these two ones, then this is going to give you some amplitude wave like this, because the amplitude or the displacement, the does displacement in the amplitude of this wave and the amplitude of this second wave, they are not equal to each other. So the resultant will be the smaller one. And the zero displacement is only possible, the zero amplitude is only possible if we have a coherent source, right? So I think you know the basic things behind it, right? So let's go into the other part. Almost all parameters related to the interference experiment, right? Now let's go to the definition of interference. And how is interference defined? It is the process of redistribution of energy of waves due to superposition of two coherent sources. Now to have interference effect, we must have at least two coherent sources. And how is it defined? It is the process of redistribution of energy of waves due to superposition of two coherent sources, right? Now if you double slit interference experiment, these two S1 and S2 are the slits, double slits, and this one is the screen. And the separation of slits, let's consider as to be small d, right? This one is a small d, and the separation of the screen away from the slits is, let's say it is capital D, or we are using monochromatic source of light of wavelength, right? Wavelength lambda, right? And it has been passed through a fine through a single slit, first of all, because the light source can emit, it gets emitted from this source, can travel in all directions. So it can go in this direction, it can go in this direction, or it can go in this direction, or it can go in all direction. But we need to have fine beam of light. That's why this single slit is helpful in passing the single beam of light. And when it strikes on the double slit part, or double slit of the substance, then the light will be interfered. It means there will be the redistribution of energy on the screen. As we saw in this case, we have maximum, minimum, maximum, minimum, maximum. It means we have bright fringe over here, that the corresponding fringe pattern is here, and the minimum indicates the dark fringe, the maximum again indicates the bright fringe, the minimum again indicates the dark fringe, and the maximum again indicates the bright fringe. So is the case in the below of the center part, right? So these are the fringe patterns, these are the fringe patterns. Now if you look at this one, we have alternate series of bright, dark, bright, dark, bright, dark, and this is the redistribution of energy, because in between the two bright fringes, the portion is dark. It means there is no light at all. There is no light at all. But in the darkness we have, but in between the darkness we have bright fringe, right? So there is the presence of light. And as I already told you, when the light gets interfered, if two when two coherent sources get interfered, then we will have such condition. Look at the fringe pattern over here. You are looking of equal pattern, right? Equal pattern. The fringe pattern is of equal size, right? So these are the fringe patterns. If we look at the figure, we'll be surprised, right? Because we have only two holes in the substance, and the light is passing through these two holes. Interestingly, we must have one brightness over here, and another brightness must be here, and all the portions on the screen must be dark. This will be totally dark, this one will be total dark, and this will be total black, because this will cast the shadow over here, this will cast shadow over, and this will cast shadow over. Only two brightness will be seen on the screen. But surprisingly, uh, we will have series of alternate bright, dark, bright, dark, bright, and dark fringes. And this phenomenon is an interference light. And this is only possible if we consider light as a wave, because through particle nature, light can only pass through this slit S1, or through this slit S2. So we can have maximum two brightness on the screen. But in this case, we have series of brightness, alternate series of brightness, darkness, brightness, darkness. And the brightness reason is due to the constructive interference. Dark fringe is due to the destructive interference. Let's go into the what is constructive interference and destructive interference. So in physics, constructive interference is defined to be two interfering coherent sources will have path difference equal to integral multiple of its wavelength. And in destructive interference, two interferent coherent sources will have path difference equal to odd integral multiple is half wavelength. So what does it mean? Let me give you an example in this case. If we take example, there this one is S1 and P, right? I have shown in the middle of the figure. Started from S1 and it is point P. The light has been started from S2 and it has reached to point P, right? So there is the certain part difference between here, because the S1P is not equal to the S2P. Obviously, S2P is larger than the S1P, so it will have some part difference, right? S2P minus S1P will have certain part difference. Now, if this part difference is equal to integral multiple of the wavelength of the light, a coherent source used in our experiment, then that's part is known as constructive interference. And if these two coherent in sources which are interfering to each other will have part difference equal to half wavelength, integral multiples half wavelength, then we will have destructive interference, right? So this is the definition of constructive interference and destructive interference in terms of physics. But if we go in the simple meaning, now you can look at the figure, right? This one is the first wave, then this one is the second wave. The crest is falling on the crest of another wave, the trough is falling of the trough of another wave, and it is adding off to give the final resultant wave. And in this case, crest and trough reinforce to each other, right? So the resultant wave will have higher amplitude. And in this case, this crest is falling on the trough of another wave, and trough is falling in the crest of another wave. So in this case, they are canceling to each other and will have no displacement at all. It means in the constructive interference, there is the two waves superimposed to give the double of the amplitude of the previous wave. And in the case of destructive interference, the two current sources are going to interfere to each other, giving the no resultant at all. And we already know that intensity I, intensity, that is brightness, is proportional to the amplitude square of amplitude in a, and we already read in our class, right? So the higher the amplitude, higher will be the intensity. The lesser will be the amplitude, the lesser will be the intensity. So in this case, the amplitude is double, so brightness will be doubled. In this case, there is no amplitude, so no brightness at all, or there is the no wave at all. That's why in bright frames we'll have higher intensity of light on the screen, and in destructive interference we will have no light at all. So that's why we will be getting alternative series of brightness and darkness in the screen.